Here I've got e to the x graphed in red, and I've got its Maclaurin series graphed in green. Now, technically this is a Maclaurin polynomial. It would be called a Maclaurin series if it had an infinite number of terms. But I'm limited to only doing a finite number of terms, and I've made that number of terms L. As the number of terms grows larger, though, the approximation gets better. This approximation is, we say, centered on 0, because that's where the two things cross, and the approximation is perfect there. As L grows, the approximation will get better and better, and it's centered at 0, so the approximation is very good here, but when you get away from 0, it starts to get worse. Of course, the larger L gets, the better the approximation gets. Now, when I get up here to 50, this is a, the red function is an exponential function. The green function is actually, a 50-degree polynomial. And it gives us a really good approximation until you get, back here. At some point, it's going to start to deviate. But if I could make L go all the way to infinity, then this approximation would be perfect for all values of x from negative infinity to infinity. But as it is, it's still really good. Now, let's also look at the Taylor or the Maclaurin series for sine. I've got that down here. Now, sine is here in purple. And again, this is a Maclaurin series for sine, and it is centered at 0. So when I put this, when I turn it on, we get a good approximation of sine here at 0. If I could make this L go to infinity, it would be a perfect approximation from negative infinity to positive infinity. So technically, again, what I've got here is a polynomial, not a series, because what I'm graphing has finite degree. Right now, the biggest value n goes to is L. Right now, that's 0. So this is a 2 times 0 plus 1 is a 1-degree polynomial. Yeah, it's a line. If I make L equal to 1, now it's a cubic polynomial. And the larger I let L get, the better the approximation is. Right now, it looks like a really good approximation. If I zoom out, you can see that it's the approximation breaks down over here and over here. But if L could go all the way to infinity, it would be a perfect approximation for all values of x. Notice right here, it's starting to choke Desmos a little bit, because what we have here is let's see, L is 50, so that means n goes up to 50, so my largest term here is 101. The degree of the largest term is 101, so that's a 101-degree polynomial. Let's dial it back a little bit to something Desmos can handle. Right here, when L is 25, this is a 51-degree polynomial. It's a really good approximation. So again, the difference in a series and a polynomial is a series has infinite degree and a polynomial stops at some point. If we could do the full series, it would be exactly the same as sine. But as it is, we're only doing a polynomial, in this case a 51-degree polynomial, and it's a very good approximation.